So in the previous few videos, we focused on how to calculate Taylor polynomials. The way I tried to line things up is I started out giving you sort of an intuitive idea for what a Taylor polynomial is and sort of explaining where the calculations come from. But then in the second video, I worried less about the intuitive side and just kind of gave you the quickest way possible to come up with the Taylor polynomial for a given function. We have these formulas that all work out really nicely and allow you to figure out the coefficients of your Taylor polynomials. So far, we've really focused on the how regarding Taylor polynomials. But in this video, I want to talk more about why. As you may have been able to tell, I get really excited about Taylor polynomials. I think they're really cool. And if you've just watched the first two videos, you're like, not all that cool. I mean, I guess it's somewhat interesting if you really like math, but it's not some mind-blowing result deserving of all the superlatives that you gave them. Well, hopefully by the end of this video, I can change that. So the first comment I want to make is these polynomials are a little bit more versatile than maybe I gave them credit for. We've built these polynomials to approximate a function near zero because that works out the nicest algebraically, but it turns out with a little tweak, you can approximate functions with polynomials at values other than zero. If you were really interested in coming up with a polynomial that closely approximates, I don't know, cosine of x, but you didn't care about at x equals 0, you cared about, I don't know, x equals 3 pi over 4. Sure. You could absolutely do that with a little tweak to the formula. It's not super interesting, so I'm not going to do it. I just want to make the comment that such a thing exists. In fact, Taylor polynomials centered at 0, in other words, created to approximate a function at x equals 0, are a special type of Taylor polynomials called Maclaurin polynomials. But whatever, none of that is really relevant. The point that I'm trying to make is just we can approximate values other than just 0. And you're like, yeah, still not impressed. Those are just approximations. I can approximate functions really well. This magical little device that I keep in my pocket. Let me show you. It's called a calculator or a phone with the calculator on it or whatever. Why do I really care about building a polynomial to approximate a function when I can evaluate the function exactly using a calculator? And well, there's lots of reasons, but one reason that might be apparent in a calculus class deals with antiderivatives. What you'll see in a Calculus 2 class is that antiderivatives, unfortunately, are pretty hard. It's harder to come up with antiderivatives than it is to come up with derivatives. And somewhat interestingly is that the antiderivative of some functions not just are hard, but are actually impossible. And I don't mean impossible like so hard that it's not realistically possible to do. I mean impossible in the sense that there is no function that represents the antiderivative of some functions. I got to be a little bit careful when I say there is no function. Really, there's no elementary function, but what you think of as a function is an elementary function. What I'm saying is if I gave you the function g of x equals the square root of 1 minus x to the 4th power, which is not all that complicated looking and really easy, fairly easy, I don't know, somewhat easy to take the derivative of. But instead of asking the derivative, I should figure out the antiderivative. You couldn't do it. And you're like, yeah, I haven't taken Calculus 2 yet. Okay, but no Calculus 2 student could do it either. Nor could any professor or any other math genius. It's not that it's hard. It's just that the function that represents the antiderivative of this is a non-elementary function, meaning you can't write it with square roots and squares and logs and exponents and trig functions and all of the other function-y things that you've learned. But as you'll see in Calculus 2, antiderivatives have this great application. They're really useful. You want to know antiderivatives. So what do you do when you're trying to figure out the antiderivative of something you can't figure out the antiderivative of? Well, one option would be to come up with a polynomial that closely approximates this function. Because antiderivatives of polynomials is something you can already do. It's not all that hard. So I guess that's kind of cool in that it makes an impossible problem possible. Although just talking about it abstractly like I'm doing here probably doesn't impress you a whole bunch. So maybe I tried to impress you up here in B and I failed, so what I can do is move on to C. And down in C, you're like, look, I'm stuck on this approximation part. I'm not impressed that you can just approximate these different functions. I like my math to be precise. I like my math to be exact. I don't like approximations. Well, here's the thing. These Taylor series are not just approximations. The more terms we add to the polynomials, the better and better the approximations get. And it turns out, and this is the part that I think is really cool, if we allow infinitely many terms in this polynomial, which is a bit of a misnomer because when you have a polynomial, you can't have an infinite amount of terms. Polynomials have finite degrees, so it would no longer be called a polynomial. But the thing you're picturing in your head as a polynomial, if it had infinitely many terms, so I don't even really know what that would look like, But if it did, these point approximations change from being approximations to exact. And that's really cool. What I'm talking about is, for this function f of x equals e to the x power, what we did is we came up with a, fifth degree polynomial, I guess it is, that approximates e to the x power. And to come up with that polynomial, we needed these various coefficients, but there's no reason we'd have to stop here. We have this very clearly defined pattern for all of the different coefficients. So we know what the coefficients on any term in a polynomial would look like. So we don't have to stop at 5. We could make a 100th degree polynomial, or 1000th, or once you get the hang of these polynomial-like things that have infinitely many terms, which is something you learn in a Calculus 3 class, you'd be able to talk about the power series, think infinite polynomial, that not approximates this function f of x equals e to the x, but is exactly equal to this function f of x equals e to the x. And that's really cool. Here's some of the math behind it. This function f of x equals e to the x works out really nicely, right? Its first derivative is the same as second derivative, third derivative, and so on. They're all equal to e to the x. So if I evaluate all those things, no matter which derivative it is, it's always going to evaluate to 1. What that means is my Taylor polynomial will take on this form that we have here. The constant term will be 1 divided by 0 factorial. The linear term will be 1 over 1 factorial. The quadratic term will be 1 over 2 factorial, and so on. And as I let n get larger and larger, this polynomial better and better approximates the graph of f of x equals e to the x. But if we didn't stop at n, if we allowed this to continue infinitely, which I know is something we can't do yet because you haven't taken Calculus 3, we'd get an exact expression for e to the x power. E to the x power is equal to this infinite sum. And yeah, it's an infinite sum, so we can't really figure it out yet, but it allows us to come up with some pretty cool formulas. E raised up to any power, whatever x is always equal to this infinite expression. So if we change all the x's in this expression into 1s, for example, I would get that e to the first power is equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 squared, or 1 over 2 factorial plus 1 cubed, or 1 over 3 factorial, and so on. If I added up the reciprocals of the factorials of all the different natural numbers, that sum would turn into e. I mean, you try it on your calculator. Take 1 divided by 0 factorial, which is just 1, and add 1 divided by 1 factorial, which is also 1, and then add 1 divided by 2 factorial, which is a half, and 1 divided by 3 factorial, which is a sixth, and do a few more of these. 1/24th, 1/120th is 5 factorial. Maybe we'll even do 6 factorial and get 720. Add up all these numbers, and what you'll get is a number that's really, really close to e, 2.71828 something. And if it's not close enough to your liking, just add a few more terms. And using the techniques of a future class, if we were able to consider the limit as n approaches infinity, where n represents the number of terms that we have in this expression, that limit would be exactly equal to e. And it's not just e that we get formulas for. Change all the x's into 2's in this expression if you want, and you'll get an infinite sum that's equal to e squared. Really what I'm trying to say is a fifth degree Taylor polynomial is somewhat useful, it's interesting, but really where Taylor polynomials become cool is when they turn into Taylor series, specifically infinite series, when you allow these polynomials to get infinitely large and you make conclusions based upon that. And it'll turn out that for some functions, the polynomial can perfectly represent the function anywhere. And for some functions, the best a polynomial can do is perfectly represent the function on a given interval. So maybe within 3 of whatever the center is, x equals 0. And that width, which kind of shows how much of the function a Taylor polynomial can create exactly, is what's called the radius of convergence. And the radius of convergence is something that you can calculate too. And what's really cool is often that radius of convergence is infinity, which means that often your Taylor polynomial, when you consider the limit as the number of terms grows to infinity, perfectly approximates your function. The function f of x equals e to the x is one such case where the radius of convergence is infinity, and a couple others that have an infinite radius of convergence are sine of x and cosine of x. Taking advantage of the fact that the derivative of sine and cosine of x just sort of cycle between negative and positive sines and cosines of x's, so that when we plug in 0, we kind of cycle between zeros and negative 1s. these formulas simplify really nicely. The sine of x is not approximately equal to, but exactly equal to x divided by 1 factorial minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial, and so on. Not that you'd ever do this, but if you really needed to know the sine of, I don't know, pi over 4, you just forgot that one off your unit circle or something, what you could do is evaluate this infinite sum, this Taylor series. I know we don't quite know how to do that yet, by changing all the x's into pi over 4s. If you change all these x's into pi over 4s, the more terms you add on to this sum, the closer and closer you'll get to the sine of pi over 4, which is the square root of 2 over 2. And there's nothing special about pi over 4. You can do that for any value. So let's see, let me choose one that's kind of interesting. The cosine of pi is equal to -1, right? We know that. So what this statement is saying is that -1 is equal to 1 divided by 0 factorial, which is just equal to 1, minus pi squared divided by 2 factorial, in other words, minus pi squared over 2, plus pi to the 4th divided by 4 factorial, in other words, plus pi to the 4th over 24, minus pi to the 6th divided by 6 factorial. 6 factorial is 720, so I'm subtracting pi to the 6th divided by 720, and continuing this forever. What you see is these terms get smaller and smaller as we go because the denominator is growing faster than the numerator. And if you add and subtract these values, there's no reason you'd suspect -1 would be your answer, but it is your answer. That's kind of wild that pi, this irrational number, when I square it and raise it to the 4th and raise it to the 6th and so on, and divide it by these different values, and add and subtract these different combinations, ends up giving me exactly -1. I mean, maybe that specific result isn't that interesting, but the point is we have infinitely many of these results that we can come up with by considering the Taylor polynomial expansions of these different functions. And it's not just sine and cosine. Anything we can take derivatives of, which is anything, we can figure out Taylor polynomials for. We look at the radius of convergence of that given function, and if it's infinite, that means that we can come up with an infinite polynomial, in big air quotes, in other words, a power series, that perfectly approximates that function, which is really, really cool. There's so much more to Taylor series. I could probably talk about this for an hour, but I think to really appreciate them, you have to understand what it means to add and subtract infinitely many things at a time, which involves a different kind of limits, which you'll learn when you take Calculus 3. So I guess I'll leave Taylor series here and hope that I've at least piqued your interest enough that maybe when you see Taylor series in a future class, you'll be more excited to learn about it.